Today we are going to learn about mathematical induction. So mathematical induction is a very important method of proof, one that can ultimately be generalized to non-mathematical contexts. Induction is a strange term in logic because it is used in two completely different ways. We've mentioned this before, but it bears repeating. In its primary sense, for philosophers anyway, inductive reasoning involves drawing a conclusion that is not deductively implied by the premises. For example, whenever I have smoked weed in the past, it has been a pleasant experience. I am smoking weed, therefore it will be a pleasant experience. This seems like reliable reasoning, but it is not deductively valid because there is no premise telling us that the future is always like the past. And that, of course, gets to the heart of Hume's problem of induction. Philosophers typically call reasoning like this inductively strong as a way of acknowledging that it is intuitively reliable, even though it falls short of being deductively valid. In this sense, inductively strong arguments that fail to be deductively valid arguments differ from the latter in two ways. First of all, inductively valid arguments are ampliative. This means that the conclusion always gives us more information than is contained in the premises. The second related point is that inductively valid arguments are defeasible. And this means that it is always possible to weaken the argument by adding more information. For example, you can weaken the inductive argument on the previous slide by simply adding another premise, like my marijuana is laced with PCP. In other words, this deductively valid argument, if I smoke weed, I will have a pleasant experience. I am smoking weed, therefore I will have a pleasant experience, remains valid no matter what new information you add in the form of additional premises. 1 and 2 deductively imply 3. So you can add any additional premise you like, such as my weed is laced with PCP, and it will still continue to imply the conclusion. You can even add a completely contradictory premise, such as I am not smoking weed, and it will still imply the conclusion. So you can apply this same type of inductive reasoning in mathematics and geometry. For example, every number greater than 1, heretofore examined, is either prime or a product of primes. Thus, every number greater than 1 is either prime or the product of primes. That's an inductive argument in the traditional sense of the term because the premise does not deductively imply the conclusion. We are simply relying on the reliability of our past experiences as a guide to the future in this mathematical context. So in the old days, before the geometer Euclid developed the notion of an axiomatic system, this is really just the way mathematics was done. Lots of interesting mathematical properties were known, in a sense, but on empirical grounds. The Pythagorean theorem was known as a result of measuring the internal angles of tons of different shaped triangles and discovering that they all sum to the same number. But this left open the possibility that someone would come across a triangle that didn't someday. So today, mathematicians are dissatisfied with this sort of reasoning, typically, because mathematics is just not understood to be an ampliative discipline in this sense. This is one of the differences between math and science. So if the above conclusion is correct, namely that every number greater than 1 is either prime or the product of primes, there should be a way of proving it with certainty. And there is, by the way. This is a theorem in number theory known as the fundamental theorem of arithmetic. So philosophers do not like inductive reasoning very much either, and many philosophical careers have been devoted to trying to explicate it as a species of deduction. This goal has actually been achieved to an important but limited degree, and one of these achievements, one we do not study in this course, is the development of what is known as inductive logic. Inductive logic is a very well-developed form of deduction based on the axioms of probability. Using it, we can, for example, deduce the exact probability that 2 rolls of a fair die will sum to 7, or the probability that you are pregnant given that you have tested positive for pregnancy using a test that is correct 95% of the time. Sadly, inductive logic does not provide a solution to Hume's problem of induction. It does not, in other words, yield any deductive proof that the past is a trustworthy guide to the future. Consequently, it does not allow us to deduce that the next time I taste sugar, it will be sweet, either with certainty or with any particular degree of probability. So ancient mathematicians were effectively in the position of arguing that a past history of mathematical observations reliably predicts the future. For example, in the dichotomy paradox, Zeno attempts to prove that motion is impossible by claiming that to move from point A to point B, one must first traverse half the distance. But before one can do that, one must traverse half that distance, and so on ad infinitum. Based on the view that it is impossible to traverse an infinite number of distances in a finite amount of time, Zeno concluded that motion itself is impossible. Zeno's argument is flawed, but not in an obvious way. It's true that you can't get anywhere if you must begin by taking a step that is infinitely small. That's just not an accurate description of what we actually do. Or to invert the point, if you were told to go from point A to point B by first stepping half the distance, then stepping half the remaining distance, etc., you would keep getting infinitely closer to B, but you would never actually reach it. Today, we say that point B is the limit of this sequence of steps as the number of those steps approaches infinity. To make his argument, Zeno ultimately relied on old-fashioned induction. He thought it was perfectly obvious that no finite number of steps could ever take you all the way to point B, but he did not deduce this. Just like with the sweetness of sugar or the soothing effects of marijuana, he had to have faith in his intuition that this process could be repeated indefinitely, always producing the same result. Mathematical induction is a deductive method that achieves some of what the ancients did not. It is based directly on the reasoning of the ancient Soriades paradox, otherwise known as the paradox of the heap. In the Soriades paradox, it is argued that if adding 1 grain of sand to something that is not already a heap does not make it a heap, then you can repeat this process forever and never make a heap. Just as with Zeno, the Soriades paradox relies on raw intuition about the future of a repeated process, but it also provides the prototypical structure of what has become known as mathematical induction. You will recall that from our previous discussion of recurrence relations, that in order to specify a unique sequence, a recursive definition must provide one or more initial conditions for the recurrence relation, the very first member or members of the sequence it defines. This is like the first grain of sand in the Soriades paradox, which in mathematical induction is called the basis, or sometimes base step. The reasoning of Soriades then asserts that if we add 1 grain of sand to anything that is not a heap, this will not make it a heap. In mathematical induction, that is what is known as the inductive step. The inductive step is to show that a conditional of this nature is true. That is, namely, if some property, such as non-heapiness, holds true at any arbitrary point k, then it must also hold true at k plus 1. Notice the discrete nature of the inductive step. This is typical of the integers and, more generally, of any set that can be well ordered, which is a concept we will expand on below. The basic reasoning pattern of the Soriades paradox is perfectly valid. However, to do mathematical induction properly, we cannot simply assert that the base case and the inductive step are true. Rather, we must prove that they are true. This requires that the predicate in question be defined well enough to yield what we call a propositional function. That is, to unambiguously map something like h of x, x is heapy, to the values true or false for every permissible argument of x. Heapiness is a notoriously fuzzy predicate that does not satisfy this requirement, and this is what seems to generate the paradox. What I mean by this is that if you were actually to try to make a heap of sand by adding 1 grain at a time, at some point you will have a collection of grains of sand, and it just won't be clear to you whether it's a heap or not. It's a fuzzy predicate because it has this gray area and no clean, bright line between heapiness and non-heapiness. So we'll now state the principle of mathematical induction. In doing so, we will loosen some of our predicate logic conventions even further regarding the proper use of parentheses and what sorts of symbols count as names and variables. In particular, to maintain consistency with typical explications in math books, we'll let n and k be variables for integers. We've already adopted the convention that numerals can be used as names, but we will further allow that other mathematical expressions like 3 squared or n plus 1 may be used as names and variables, with parentheses added for convenience for the purpose of disambiguation. So here's the principle of mathematical induction. Let P be a property such that Pn is a propositional function for n is an element of z plus. And it could also be that n is an element of n. So this stipulation contains a lot of information and a lot of restrictions, so let's just make it clear. P has to be some property that is not like heapiness. It has to be a very well-defined property, and it only applies to some entity that is either a natural number or positive integer, or something that can be made discrete in that way. So a grain of sand is discrete. Heapiness is not good enough to be a propositional function, but we can talk quite meaningfully and clearly about 1 grain of sand, 2 grain of sand, 3 grain of sand, 4 grain of sand, etc. So let P be a property such that Pn is a propositional function for n being a member of the positive integers. So to show that for all n, Pn, so that to show that everything, every value of n has this property, we have to do the following. We have to do the basis step, and we also have to do the inductive step. So the basis step simply requires us to plug 1 in for n. So pk is true where k equals 1, and actually show that it comes out true. And the inductive step, we show that if it holds for all k up to some point, then it must also hold for the very next one. That is to say, k plus 1. So I just note here, this is a slightly restricted definition for the sake of clarity. In reality, the basis case is often 0 rather than 1, in which case n is an element of the natural number. So before looking at some examples of mathematical induction, it's important to ask why we are so sure that it is a valid method of proof. And this is actually what I would like to stick from this lecture. The examples are interesting, but what we're really interested in philosophically is why we are assured of the deductive validity of mathematical induction. And it's important to understand that at this point, we actually haven't done that. We've stated how mathematical induction works, but we have not demonstrated that mathematical induction is a species of deduction. So after all, put in the form of a predicate logic argument, the principle of mathematical induction appears to be this: P of 1, premise 1, premise 2, for all k, if pk, then p of k plus 1, therefore for all n, Pn. But this is not a recognizably valid inference pattern. If we do predicate logic on it, it's going to look like this. We have our 2 assumptions, okay? And then we can do universal elimination on 3, fine, okay? So now we know that P of 1 plus 1 by 1, 3 conditional elimination. We know that 1 plus 1 is 2, so now we know it's true of P2, but then what? Well, you could eliminate 2 again and get 3, right? Eliminate 3 and get 4. But that's just a process that goes on forever. And also, to be clear, if you tried to do it by negation introduction, you would never produce a contradiction. So far, this just has the same defects of any intuitive argument like Zeno's that says, well, clearly, if you continue doing this forever, you're always going to get the same result. So it turns out that the validity of mathematical induction can only be demonstrated on the basis of a specific property, one that is exemplified by sets of numbers, and specifically sets of integers. This property is not implicit in the rules of predicate logic itself. At bottom, the property in question is the property of having a least member. Obviously, this assumes the relations of greater than and less than. You can't talk about something being least. In other words, those are implicit in the concept of least, but it also assumes a discreteness to the objects in the set, a property we find with integers but not with, say, the real numbers. And the discreteness we're really talking about here is the space in between them. There is no number at all between 1 and 2, as long as we're talking about the positive integers or the natural numbers. But when you're talking about the rational numbers or the real numbers, there's an infinite number of those between 1 and 2. And in fact, there's an infinite number between any two arbitrarily selected rational or real numbers, no matter how close they are together. That's what we mean by them not being discrete. So in set theory, the general property displayed by sets of integers or natural numbers is that they can be well ordered. What this means intuitively is that they can always be placed in ascending order, meaning that there is always a next member until, with finite sets, you get to the last one. But the usual way to define a well-ordering of a set is that every non-empty subset will have a least member. While obviously true of sets of integers, this is not true of sets of real numbers because, and here I need to explain some symbolism to you, this is a way of talking about an interval, and the smooth parenthesis means one thing and the square bracket means another. So if I were to write, and this is not ordered pair, this is interval. So roughly it's indicating all of the numbers between 0 and 1. But the smooth parentheses is called an open interval, which means that it does not include 0 and 1. But the bracket, the square brackets is closed, a closed interval, which means that it does include 0 and 1. So if we mix them like we do here, we're saying it does not include 0. The interval does not include 0 itself, but it does include 1. Okay? So sets of real numbers, because the open interval, that is, and this is the set theoretic expansion of this, that is the set of all x is an element of real numbers, such that x is greater than 0, but then less than or equal to 1. So if we think about that interval, which is equally well expressed by this and this, by both of them. So if we think of that interval, it's a perfectly well-defined set, but it does not contain a least member, and that's because you can keep getting closer and closer to 0 in Zeno-like fashion. But since you never get to 0, because there's always a real number arbitrarily close to 0, there is no way of selecting a least member. So if we allow ourselves to access to the notion of a least member, then the proof of the soundness of mathematical induction is straightforward. It is an indirect proof which requires us to define a set S of positive integers that do not possess the property P in question. So we define this set. S is identical to the set of all n that are elements of Z plus that do not have P. So the reason you do this is because in the indirect proof, you assume that the property in question does not hold for all n. And if it does not hold for all n, then this set must exist, the set of all things that do not have that property. So we'll just post this definition at the top of the proof, and then we can see how it works out. All right. So now if we take another look at the proof, but we proceed by negation introduction, we have the assumption, say that the number 1 has the property in question, and we also have the assumption, the inductive step, that for all k, if k has the property, then the very next thing, k plus 1, has the property. And from this, it seems like it follows that everything has the property. We saw that 1 and 2 were not sufficient to secure that conclusion. So let's assume now that it's not the case and try to generate a contradiction on the basis of this set. Okay, so we assume it's not the case that for all npn on step 3, we apply quantifier elimination to get there exists an x such that not Pn, and then we do a hypothesis for existential elimination. So we'll go to not Pa. And now, since we've hypothesized that there exists an x such that not Pn, and since S is the set of all n that are members of the positive integers such that not Pn, we know that S is not identical to the null set. So on line 7, we say we're entitled to conclude from the fact that S is not identical to the null set that there exists some x such that x is an element of S, and for all y, if y is an element of x and y is not identical to x, then x is less than y. Now what this basically is just saying is that the set S, which is a subset of the positive integers, has a least member. Now we don't know that the least member is A, of course, but we know that if it's not A, then we know there's something else in something else in S that is the least member. So A is the least member, or there's something else in S that it's the least member. We know that it has a least member because of what we have called the well-ordering principle, which tells us that among other things, that the positive integers are well ordered. Okay, so there exists an x such that x is an element of S, and for all y, if y is an element of S and y is not equal to x, then x is less than y. So x is by definition the least member of S. So now, of course, you can just do another hypothesis, an existential elimination hypothesis for 7, and you will go to B here rather than A. So we're just following all of our basic rules for inference and predicate logic. And then here, from 8 to 9 is the critical insight. You see what's being said here? So remember that S is just all the numbers that don't have the property. And the only reason we're talking about S is because we're involved in an indirect proof that assumes that it's not the case that everything has the property, meaning there are some things that don't have the property, and we're expecting this to generate a contradiction. So B is the least member of S. But that means there's going to be an element prior to B, right, an integer prior to B that does have that property. So B minus 1 we know has the property. Why do we know it has the property? Because S is the set of all the numbers that don't have the property. So we've already got the assumption that 1 has the property, right? So b minus 1 could be 1, and if it's not 1, then it's going to be a number greater than 1. But, right, so that's the really critical and important thing to see, is that once you've defined the least member of S that doesn't have the property, there is definitely something before it that does have the property. But now can you see what's going to generate the contradiction? If you look at, again, line 2, if you instantiate 2, right, to b minus 1, which remember is just the name of some number, we get for all k, p of b minus 1, if p of b minus 1, which we know to be true, then p of b, right? Because b is the very next one. And that, of course, gives us pb and not pb from conditional elimination on 9 and 10, and the definition of S, which using existential elimination has told us that B is the least member of S that does not have the property P. So the rest of this is just cleanup work with getting rid of your hypotheses, which you all know how to do. It could be useful to review the structure of this just in English. So if you were to state this proof in English, it would go like this. Assume that some propositional function Pn has the value true for both the basis step n equals 1 and the inductive step, but it is not true for all values of n. That's your indirect proof hypothesis. Then we can define a set S that contains all values of n for which Pn is false. But we know from the well-ordering principle that S is well-ordered, hence S must have a least member. Call this least member B. By the definition of S, PB is false. Now consider the integer b minus 1 immediately preceding b. We know that p of b minus 1 is true, otherwise it would be a member of S. But as we have assumed the inductive step is true, it follows that PB must be true as well. Hence, PB is both true and false. QED. So, what prevented the ancients from explicating mathematical induction as a form of deduction was that they had not developed the conceptual resources to think deeply about the properties of integers. We should emphasize that we are still cheating a bit here in the sense that we have just helped ourselves to the fact that the integers are well ordered. In some ways, this comes down to the fact that we are cheating by doing set theory naively rather than axiomatically. But even standard Zermelo-Fraenkel set theory cheats on this particular issue by simply adopting a once controversial axiom known as the axiom of choice, which implies the well-ordering principle and is equivalent to a much more powerful idea known as the well-ordering theorem. Now, when I say cheats in quotes here, I don't mean that there is anything unacceptable going on in mathematical terms at all. This is just how axiomatic systems work. Axiomatic systems rely on a set of generally intuitively plausible fundamental propositions, and everything else that is true can be theoretically derived from those propositions. If axioms are really, truly fundamental, then there is no way to prove them, though if the set itself is inconsistent which is to say it implies a contradiction, that we do know that at least one of them has to go. So none of this is really relevant to establishing the validity of mathematical induction. The well-ordering principle can be established for sets with cardinality aleph null. That's the Hebrew letter of the first letter of the Hebrew alphabet, aleph. And aleph null, as we'll see later, is the cardinality of the integers. So as you know, the integers are an infinite set, so this is a particular infinite cardinality, which we'll be talking about more later. So before looking at a few examples of mathematical induction, we should note that there are two distinctly different forms of it. What we have just been discussing is sometimes called weak induction. There's another form called strong induction. Most important thing for a philosopher to understand about them is that they are logically equivalent. The reason one is used rather than the other only has to do with mathematical convenience. With regular or weak induction, as we saw, the inductive step is to show that if pk, then p of k plus 1. This amounts to showing that for all k, if pk, then if pk plus 1, since k is in effect chosen. With strong induction, the basis step is the same as for weak induction, but the inductive step is to prove if for all x, if x is less than or equal to k, then px, then p of k plus 1. So here the antecedent condition for all x, if x is less than or equal to k, then px, is just explicitly stating that px is true for every x less than or equal to k. It sounds like a stronger assumption, hence the name, but it is no different than stating that pk is true for any arbitrarily chosen k. So in mathematics, lots of proof by induction come about because we think we have noticed some kind of pattern. For example, we noted previously that every number greater than 1, heretofore examined, is either prime or a product of primes. This result has been proven by mathematical induction, which is why we now call it a theorem rather than a conjecture or a hypothesis. It is also true that every even number greater than 2, heretofore examined, is the sum of two primes. Goldbach's conjecture is the claim that this is necessarily so. It is still a conjecture because nobody has ever been able to prove it. So let's try to prove a different observed regularity, namely that the sum of the first k odd numbers is k squared. This is an interesting property that you've probably come across in the past. So for example, 1 plus 3 plus 5 plus 7 is 16. There are 4 numbers, and 4 squared is 16. So we could use the summation sign, and we would write it like this. 2k minus 1 is the formula that gives odd numbers, right? You put 1 in, and you get 1. You put 2 in for k, and you get 3. You put 3 in for k, and you get 5, etc. So that's a way of generating the sequence of odd numbers, and through sum n equals n squared. So this is something that seems to be true when we keep adding up sequences of odd numbers, but the question is, can we prove it to be true? And the answer is that we can prove it to be true, but we've got to use induction. So what do? Well, the first thing you do is you prove it for the base case. The first odd number is 1, and of course, if you put that in the formula, you get 1. So that's the easy part. The inductive step is just a little bit trickier. What we do is we assume that this property holds for some arbitrary number k. And so we could represent it this way. We got 1 plus 3 plus 5 up to some, which we can only represent by our formula, 2k minus 1. And so we assume that up to some arbitrary k, the relation holds that this equals k squared. And now what we try to do is we show is if it holds for some arbitrary k, then it must hold for k plus 1. So if we rewrite this, this is what we're trying to prove here, right? We just have the previous sum up to k, and then we have to write in, right, the value when we substitute k plus 1. So if 2k minus 1 is the previous value, the next odd number is 2 greater than that. So if you add 2 to take 2k minus 1, you get 2k plus 1. And so what you need to show is that this is identical not to k squared now, but to k plus 1 squared, right? So if it holds for any arbitrary k, which is represented here, then it holds for k plus 1, which we represent by adding k plus 1 here and representing it as k plus 1 squared. So that's the setup, and the setup is what's most important philosophically. The rest of it just comes down to doing some math. And sometimes this math is really difficult, and it relies on a lot of tricks that mathematicians learn, but philosophers and sometimes even logicians do not learn. In this case, though, it's actually pretty simple, which is what makes it a nice example. So as we've just said, we're just repeating ourselves now. If 1 plus 3 plus 5 plus 2k minus 1 equals k squared, then we need to show 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1, which is the very next odd number, the result of plugging k plus 1 into this formula. In case I'm not being explicit enough here, right, you get this number right here by calculating 2 times k plus 1 minus 1, right? So that's 2k plus 2 minus 1, which is 2k plus 1. So now we can just do a little bit of identity substitution. We know k squared equals this, so we can substitute k squared for the preceding part, the yellow formula, right? So we know now that k squared plus 2k plus 1 equals k plus 1 squared, or at least that's what we're trying to demonstrate. Trying to demonstrate this is identity, and you can see this is just math. And if you remember how to do polynomial expansions a little bit from high school, then you know that this is just k squared plus 2k plus 1 just is k plus 1 squared. And so that's how that simple inductive proof works. Now, if we return to Zeno's dichotomy argument, we might, after fooling around with this progression for a while, conjecture that 1/2 plus 1/4 plus 1/8 plus 1 over 2 to the n equals 1 minus 1 over 2 to the n. It works great for k equals 1 and k equals 2 and k equals 3. And if we can prove this is indeed the correct formula, that is, this is the way it must be for any value of k, then we will also have proved that Zeno only intuited, namely that every finite, we will have proved what Zeno only intuited, namely that every finite value of k will yield a result less than 1. So the math for this is a little bit more complicated, but the setup is relatively straightforward again. So again, you just apply the basis step, which would be k equals 1, perform the computation, which comes out to 1/2, and of course, 1/2 is less than 1. So being less than 1 is the property we're interested in, and that has been demonstrated. Now for the inductive step, we hypothesize again that it's true for some arbitrary k that 1/2 plus 1/4 plus 1/8 plus all the way up has this property. And notice here we have 1 over 2 to the k, because 2 to the k is what generates the halving property, right? If you just look at the denominator, 2 squared is 2 to the 1 is 2, 2 to the 4, 2 to the 2 is 4, 2 to the 3 is 8, etc. So we're going to hypothesize that this up to some arbitrary k is identical to 1 minus 1 over 2k, right? And then as before, we need to just prove that it follows for k plus 1. So what's that going to look like? Well, again, here the previous sequence is all now in yellow down here, right? And so we're assuming that this is that, right? And the very next one is just going to be 1 over 2 to the k plus 1, and that's identical, we're claiming, to 1 minus 1 over 2 to the k plus 1. And so if this is true, we should be able to demonstrate this identity mathematically. Now again, as far as philosophy is concerned, this is what's interesting. We know what it would take to actually prove this by induction. The fact that it can be proven is also important, but it's important mathematically. Remember, just as before, we're going to substitute this for this, and as a result, we come up this. I've just got what we're trying to prove up here to remind ourselves. And so in this case, you just have to remember or learn how to be able to add fractions together. The only way you can add fractions is by creating a common denominator. So what would do that in this case is multiplying this by 1, right, in the form of 2 over 2. You need to be able to remember or learn that if you multiply n times n to the k, that equals n to the k plus 1. So it gives us this identity, which simplifies to 1 minus 1 over the 2k plus 1. Okay, so this is just all math, but the important part is the inductive process itself. So the ability to do inductive proof in math depends entirely on one's mathematical training and competence. Inductive proofs are interesting to philosophers and logicians, mostly because they can be used to prove that our languages and derivation systems have particular logical properties. For example, to show that a particular system is sound or complete, we need to be able to show that the property in question holds for a tree or a proof of any length. It is because the growth of a formula, tree, or proof occurs in discrete steps that it can be described as a well-ordered set susceptible to mathematical induction. To take a simple example, consider the series P, not P, not P, not P, not P, etc. In other words, the result of repeatedly adding the negation sign. How do we demonstrate that every member of that series, no matter how long, is a woof? It might surprise you that we need to demonstrate that, but if you really take metalogic seriously, that's something that you need to prove. It seems like it's obvious, but you don't want to be like Zeno and just say, well, see, clearly, if you just keep doing that, it's always going to be a woof. For any given finite woof, you can apply the formation rules to determine whether it's a woof But what we're really asking about here is whether it will always be a woof if we continue to do this or that. The answer is that we use the formation rules for propositional logic together with mathematical induction. The basis step, very simply, right? The very first member of the series, P, is a woof. Okay, so that's simple. The inductive step says assume some arbitrary K of this series is a woof, show that K plus 1 is also a woof. So this is much simpler than our previous examples. In this case, K plus 1 equals simply negated K. And negated K is a woof by the second rule for the formation of woofs, which says that if A is a woof, then not A is a woof. And that's all there is to that. Now, of course, proofs in this area in logic can also get very complicated because not all the properties are as simple as something like negation. So finally, as you might suspect, mathematical induction is essential to proving many results in set theory. As an example, which I won't actually talk about because I think it's going to get a little bit tedious, though I'll show you the slides that demonstrate it. Consider the conjecture that for any set S with finitely many members n, the cardinality of the power set of n equals 2 to the n. Now, if you were to apply this to the null set, you would see it's true. If you were to apply it to a set with one member, you would see it's true. If you were to apply it to a set of two members, you would see it's true. So it seems like it is true. But to really demonstrate that it's true, you would have to use mathematical induction. So how would you prove that every set S with finitely many members n has 2 to the n subsets? Well, first you would do the basis step. The basis step is just the null set, right? So the null set has 0 members. 2 to the 0 is 1. So where a set has n equals 0 members, the cardinality of its power set is 2 to the n equals 1. The inductive step, you would assume that every set with finitely many members, k, has 2 to the k subsets. And then you'd show that it follows that any set with k plus 1 members has 2 to the k plus 1 subsets. Now this is a non-trivial task that requires remembering some of the properties of sets we've learned. So first, let's note that 2 times 2 to the k equals 2 to the k plus 1. We actually used that property in a previous demonstration. So it is wise to suspect that we might take advantage of this fact. You just never know. And let's give the set with k plus 1 members the name T, and the member we've added to S in constructing it the name C. So note that T then may be described as T equals S union the set that contains C. Now, these are obviously true when we say them, but it's not at all obvious that this is the way that we should frame things. It just so happens that framing these things in this way is what allows us to prove it most straightforwardly. So then suppose that in constructing the power set of T, we have first constructed the power set of S. Now, the only remaining subsets to construct will all involve C. Specifically, the remaining sets are, and this is a mouthful, but the set of all x such that x is a subset of T, right, meaning x is a subset of this union, and limited to this property, because we don't want to produce the sets we've already produced by constructing the power set of S itself. So, and there exists a y such that y is a subset and x is identical to y union the set that contains C. So that's a way of characterizing all the remaining subsets of the power set of T that are not members of the power set of S. So in English, the remaining members of the power set of T resulting from creating the union set of each subset of S with the set that contains S. So this means that in creating the power set of T, you're essentially doubling the number of members in the power set of S, because you're joining every subset of S with the set that contained C. Okay? So since by the inductive hypothesis, the cardinality of the power set of S equals 2 to the k, it follows that the cardinality of the power set of T is 2 times 2 to the k, which is 2 to the k plus 1. And although this is not part of the proof, it helps you to visualize that for an arbitrarily selected finite set. So if set, well, not arbitrarily selected, because we selected for it to be manageable and small, but if S were identical to the set that contains AB, that would mean that T would be one more the set that contains ABC. So if we took the power set of S, we would get the null set, the set that contains A, the set that contains B, the set that contains AB, and then when we finish off creating the power set of T, that will simply be a matter of creating a union of the null set with the set that contains C, set that contains A with the set that contains C, set that contains B with the set that contains C, set that contains AB, the set that contains C, doubles the number in the power set of S, right? So we have 2 times 2 to the k equals 2 to the k plus 1. And that's it for our lecture on induction.